IEM Society Branch, Student Branch Chapter. To start off with the inaugural session, I would now like to introduce before you our convener of the FDP, Professor Dr. Moutushi Singh ma'am. Dr. Singh ma'am is head of the Department Computer Science and Engineering and Computer Science and Engineering AI. Madam has several publications in renowned journals and conferences to her credit. Dr. Singh's research area includes wireless communication. I would now like to invite ma'am to kindly address the gathering. Over to you, ma'am.
Thank you. Thank you, Shubhasri. I think I am audible and visible both.
Right, you are.
Good afternoon, Sharbani madam. Welcome to
Good
IEM.
afternoon. Thank you.
Okay. So, ladies and gentlemen, good afternoon and a warm welcome to this faculty development program on emerging trends and the challenges in cloud computing and the Internet of Things. So it is a privilege to stand before you today as we embark on this journey of exploration and learning into the most transformative fields in modern technology. The rapid advancements in cloud computing and IoT are reshaping our world. From how we manage our personal lives to how the business operate and innovate everywhere, we are finding the cloud computing and IoT usage. These technologies are not only driving efficiency and productivity, but are also opening new avenues for research, development, and societal impact. In cloud computing, we are witnessing a remarkable shift towards multi-cloud and hybrid cloud strategies. Organizations are leveraging the strengths of different cloud providers to optimize the performance, cost, and security, ensuring they are not confined to a single vendor. This strategic diversification is becoming essential in today's dynamic digital environment. You can also find edge computing here. It is another significant trend, pushing data processing closer to the source of data generation. This approach reduces the latency, improves response times, and decreases the bandwidth usage, which is crucial for applications that demand real-time processing. Like you can find the autonomous vehicles, the industrial automation, etc. Now, however, with these advancements comes significant challenges also. Security and privacy remain paramount concerns. As data breaches become more sophisticated, protecting sensitive information and ensuring the compliance with regulations like the different protocols is increasingly becoming very complex. Think about the cost management, the interoperability, and integration usage persist as organizations adopt multi-cloud and hybrid environments. So you can say that. So there are so many challenges, so many trends, and we are having experts in different domain of obviously of this issue. They will come and deliver their thoughts in this FDP very much. So in conclusion, I should say the field of cloud computing and IoT are at the forefront of technological innovation, presenting both exciting opportunities and formidable challenges. So this faculty development program aims to delve deep into these topics, providing you with the latest insights, trends, and solutions to navigate this evolving landscape. I encourage you all to actively participate, engage in discussions, and share your perspectives. Together, we can foster a collaborative environment that promotes learning, innovation, and the advancement of knowledge in cloud computing and IoT. So thank you for being here, and I look forward to a productive and enlightening program. Let us embrace the future of technology with curiosity, determination, and a spirit of collaboration. Thank you. Thank you, Anne. And over to ma'am.
Thank you, ma'am.
Thank you.
Thank you for the yeah. So thank you very much, ma'am, for the wonderful address and why we need to be attentive and thoroughly going to enjoy the session coming up for the 5 days. Now it is the right time to begin our faculty development program with our first speaker. And on the onset, we have our eminent speaker, Dr. Shubhasri Roy, Professor, Department of CSE, Jadavpur University, Chairperson, IEEE Computer Society Chapter, Kolkata section. Dr. Roy completed her postdoctoral research as a Fulbright Nehru uh, Fellow at Department of Electrical and Computer Engineering, the University of North Carolina, Charlotte, USA. She pursued her PhD in Engineering, Department of Computer Science and Engineering, Jadavpur University, Kolkata. She is recipient of several awards, few of them includes Fulbright Nehru Senior Research Fellowship. She was awarded, but she did not avail UGC Raman Postdoctoral Fellowship 2013-14, Best Paper Award in the International Conference on Electronic Systems, Signal Processing and Computer Technologies, Nagpur, India on January 2014, to name a few. I would like to express our gratitude to ma'am for accepting our invitation and gracing this occasion with your distinguished presence. Now I would like to request ma'am to talk on the topic today. Ma'am is going to deliver us the speech on knowledge-based system using IoT cloud. Over to you, ma'am.
Thank you, Shubhasri. Thank you so much. Uh,
Welcome,
first of
ma'am.
all, first of all, I would like to thank Dr. Moutushi Singh, Rounak, for having me here, and all the organizers of this FDP program. I just want to make a small correction in my introduction that currently I'm not the chairperson of Computer Society Kolkata section IEEE. Currently, Professor Nivarun Dash is the chairperson of IEEE CS. I was last 2 years. So that is the small correction from my side. Uh, I hope all of you can see my slides. It's visible, right?
Right, ma'am.
Okay. So for the better uh, network connection, I just want to turn off the camera. Hope it is fine. So, uh, this FDP program is on emerging trends and challenges in cloud computing and IoT. Uh, Keeping the main focus of the FDP, I have decided to deliver a talk on knowledge-based systems using IoT cloud for air pollution monitoring. So basically, uh, I assume this is the first talk of this FDP program. So my intention here uh, is to share my research experience uh, uh, of utilizing modern technologies like IoT cloud, building an end-to-end system, knowledge-based systems for some social good applications. As I have only 1 hour time today, so I have picked a particular application and it's an air pollution monitoring application. So usually in the last 5-6 years, my research interest mainly focused on uh, application of technologies for social good. So when I'm saying social good, I'm actually trying to highlight some of the applications which are very much linked with our day-to-day life. For example, our health, environment, education, traffic and transportation, overall the quality of life. And when we are exploring different type of modern technology, or when we have this idea of different uh, advanced techniques, we can also understand how we can utilize them for solving different problems. So in today's lecture, I have picked one such type of problem, uh, which is related with the environment, and my focus will be on air pollution. And this particular study is also very important from the current climate change and other environmental risk point of view. Now, I believe that uh, technology for social good is a very important aspect in the current scenario. You can think about any technology. Uh, Broadly, we can say the information and communication technology. So these two are actually the pillar of technologies based on which we can develop several solutions, which is also known as ICT, information and communication technology. And by utilizing this information and communication technology, we can develop several type of solutions. Several type of solutions. We can address several type of problems that are actually for social good. So these two terms are very, goes quite well with each other. In social good applications, we can put climate change and environment related applications, healthcare, smart city, self-driving cars, natural language processing, and many more, which has social impact. Now, uh, if we think about any particular solution where we can develop a system, information and communication technology based system, to address any such social good application, in for today's, I have picked air pollution, which is essentially part of the climate change and environment category. We can build an end-to-end system based on information and communication technology. And in information and communication technology, majorly the major components that are required are like IoT, Internet of Things, cloud or distributed computing frameworks, artificial intelligence, uh, which is the predictive analysis based on the statistical approaches, machine learning approaches, deep learning approaches, data science, data visualization. So these are different technologies or components which can be used or which can be harnessed to design and develop an end-to-end system for this kind of applications. Beside that, there is another very interesting factor which is called participatory sensing. We all know that how to utilize the sensors, which are probably part of the different type of devices, maybe your mobile phone or maybe any IoT device. Beside that, in the current situation, uh, sorry, I'm getting some noise. Is it
Yes, ma'am, I have muted the
okay?
participant.
Okay. Okay. So participatory sensing is from this term, it is a sensor where the human beings are considered as a sensors. They can act as a sensor, and there are several terms coined to highlight the importance of this particular um, component, like crowd sensing, crowdsourcing, or participatory sensing, or citizen-based sensing. The different type of terms are coined for that. In the current situation, participatory sensing or the crowd sensing is also a one very essential component for this kind of design, beside IoT, cloud, AI, and data science. And there's a one very interesting line I read in a review on smart city, and it is like technology and data are key enablers. So these two things are very important. We need a very good, smart, efficient technology, as well as we need data. But without the smartness of people, proper engagement will not be achieved, and smart city projects fail. So that is a very interesting phenomena. Many cities and companies have also learned this lesson and turned their strategies 180 degrees. So whatever system, whatever solution we design to solve any problem, we also need to keep the citizen or the people in the loop. Their participation their intelligence can also add an um, extra line in the whole system. So that is a one very interesting thing. Now, I will tell some of the very popular applications where we need IoT, cloud, AI, data science, all these things. One very popular such type of application is autonomous vehicle. So in autonomous vehicle, several vehicular companies like Tesla, BMW, Mercedes, many companies are there. They are working on this project of autonomous vehicle or self-driving car. Tesla is very popular in this domain. And if you think about the overall concept of the self-driving car, you will find that it's actually about the sensor technology. Different type of sensors are there: accelerometer sensor, gyroscope, magnetometer, lidar sensor, camera sensor, thermal sensor. Different type of sensors are there. So these sensors are actually trying to capture the environment as much as possible. They are trying to get the entire environment in front of that vehicle. They're trying to analyze that environment, and based on that analysis they are taking decision. So this kind of system is nothing but a knowledge based system where we have different type of sensors to capturing the environment. Those data are actually get analyzed, and from that knowledge actually inferred, and it is providing the system a strength so that it can fulfill the requirement of a self-driving car. So this is one very popular example. Another very popular example, little bit in a different domain, in the domain of the healthcare, is precision medicine. Precision medicine is a very interesting idea where researchers are using this concept of deep phenotyping. In the deep phenotyping, the different type of patients, um, they are actually categorized based on their uh, different different properties, based on their lifestyle, their different medical situations, uh, and according to that, some precision medicines are used for the for their well-being, or for the personalized health promotion, or for any chronic disease prevention. So that is another very interesting application. But in the background of this kind of application, it is actually dealing with a huge amount of data. So big data analysis and integration of um, that with the different type of AI based mechanisms for the prediction, for the analysis of specific medical related properties of that particular person. These things are very I mean very interesting how they are combined together, and they can pinpoint the issue so nicely so that they can provide this personalized health promotion, or they're able to detect chronic diseases. The third application that I have is little bit focused on computer vision. So this is actually in Africa. They are using this kind of solutions to catch the poachers. So basically, they have a drone equipped with the camera, and the drone camera can capture the images, as well as it can classify, it can detect the objects or the subjects. For example, here the elephant and the poachers also, which will be geo location enabled with the geo positions. And then that after processing that, after identifying the poachers, it will send that information or some messages to the local community. They can then take some actions to stop these poachers from being making any such actions. So this is another very interesting application where you can see that drone, which is equipped with sensors, which is also having the power of analyzing that uh, uh, images, and able to identify the objects, and then mm, um classify it, and then send some action, send some messages to the local community. So sensors, uh, AI models, and then the communication to the local community. All these things are part of it. Now, if I come back to this concept of knowledge-based systems. So when I'm talking about the knowledge-based systems, I have highlighted few points for this, and these are few things that I think we need to understand when we are designing any knowledge-based system. The first point is acquiring data. So whatever the application is, we need to acquire the data. For example, in smart vehicle or a self-driving car, we need to acquire data to understand the environment. For precision medicine, we also need data about that person, its medical condition, its other lifestyle, and all these things. So acquiring data is the first and essential point from where we need to start. This part, if we think it from the technology point of view, we need sensors, we need Internet of Things or IoT devices for this. These are actually very low cost, lightweight devices. IoT, usually when we use the term IoT, we try to design um, IoT devices as a very low cost and lightweight. When they are low cost and lightweight, they are also becoming resource constrained. So resource constrained in one issue here. The second step, so keep this challenge in mind that IoT devices are usually resource constrained. Now, when they are using to acquire the data, they are utilizing the sensors, they are acquiring data. It could be continuous or periodic, but there is definitely a huge chance of getting big data. So for that data, we need to store it, and we need an environment where you can analyze that. So storing data and computation is the second step. For storing data and computation, we need storage and processing. However, the IoT devices, it's just a low cost and lightweight. They are resource constrained in terms of storage and processing. But the data they are generating is very big and huge in size. To store and process that, we need cloud environment. So cloud computing or distributed computing environment is providing the infrastructural support to this type of systems where there is a chance of generating big and huge data. After that, once you acquire the data, you store that data in a cloud environment. After that, you need the proper organization of the data. For that, you can use SQL or NoSQL databases, where the most important performance metric is the response time, because you want to provide a solution, or you want to provide a service where it will be in the real time systems means very less response time. And that again depends on data integration. How good data is integrated, it's based on that. Next step is analyzing that data. Different type of predictive analysis or data mining techniques can be performed here. They can be implemented parallelly or distributedly, so that they can achieve high performance. For predictive analysis, data mining, different type of AI and data science approaches can be used. Next step is inferring knowledge. For inferring knowledge means new knowledge from existing facts. So when we are getting more data, that data getting bigger, we can have uh, some more information there, and we may able to design models that can infer knowledge in a better way, where the accuracy is very important. So again, here you can apply different type of AI and data science approaches. And after that, making decision. For example, what should be the optimal outcome, how efficient your approach is, all these things. So that again, part of the AI and data science. And finally, when you have all these things, you can provide some services. For example, any forecasting or recommendation services. So when you are providing services, actually you are utilizing all these technologies. So this is called technological convergence, where you have IoT, you have cloud, you have the models using AI and data science techniques, and then you are providing some services. That is the technological convergence. So this is a very simple view of knowledge-based systems. Now, what are the main components to build an end-to-end knowledge-based systems? The first step is the IoT device, which consists of different type of sensors. Uh, it depends upon a particular problem. For any particular problem, for example, as I'm talking about the air pollution monitoring, so we need some sensors that can measure the different type of pollutants, for example, PM 2.5, PM 10, or SOx, UX, like that. Then required the communication. Communication means here two type of communication is important. One is the device to device communication, when from one node to another node, that type of communication is required. Another is the device to cloud communication. That means from device, it may transfer it to the cloud, and from cloud, that could be provided as a service. For storage and processing, distributed environments like cloud, edge, fog, distributed and high performance computing. These are the uh, components which are associated with. Then comes the mobile app or web app, front end and back end. For that, different type of uh, frameworks are also used, like React or Spring Boot or Node.js or backend services, uh, Firebase or DynamoDB. Different type of services can be used. And for predictive analytics, it's a very big domain. Based on the requirement of your application, you can, if you want to provide any forecasting, if you want to provide any predictive analysis, you can, based on the nature of the data, you can pick the model, or you can train your model. You can tune your model to perform a better performance, to provide a better performance. And in some domains, there are very good pre-trained models are also available that you can also use for predictive analytics. So different type of solutions approaches are available here. So now I'm moving to the application side, social good applications. As I told you, I categorize social good applications are applications which are somehow linked with the people. And here I have considered the city dynamics. And under city dynamics, air pollution, noise pollution, traffic condition, road condition, mobility pattern. These are different factors which are associated with a city or a smart city. And if you want to study the dynamics of a city, these are the aspects of a city that actually directly influence a citizen's quality of urban life. Now, as I don't have much time, so I have focused only on this air pollution part. Air pollution is a very big problem in our country. It's not a problem for our city. It's actually a problem of most of the major cities of India, being Kolkata, Delhi, Mumbai, Bangalore nowadays also. So hugely affected by the air pollutions. So air pollution is a big problem. There is no doubt about that. Now, if we think uh, about a system where we can utilize these technologies, IoT, cloud, a little bit of AI, data science, all these things, uh, how we can develop that systems. So for Internet of Things or sensor modules, there are several type of modules that are used or that are available, like weather monitoring sensor, pollution monitoring sensors, biometric sensors. We need the microcontrollers and developer boards. Popular microcontrollers and developer boards are like Arduino Uno, Mega. Then Expressive developer boards are also there. Then Raspberry Pi boards are also very popular. Uh, Beside this board, so we need this microcontroller or developer boards. Along with that, we need sensors. And we also need communication modules like Wi-Fi communication module or Bluetooth module or GSM GPRS module. Now, if we look at the IoT stack, this IoT stack is not very different from the standard TCP/IP protocol stack used in networking. If you look at this diagram, you can see that there are two stacks, right? So the left part is unconstant and the right part is actually constant. Left part is unconstant means there is no limitation over the resources. The resource availability is as usual. So what we have the physical layer, 802.3, 802.11, Ethernet and Wi-Fi wireless LAN, then IPv4, IPv6, TCP, UDP, and so on. So this part is quite familiar to us. For constant part, that means where the resource constraint is the problem. In that part, you can see that in the data link layer, 802.15.4, which is actually the Zigbee, and the 802.15, which are actually used for uh, low power personal area networks like Zigbee, Bluetooth, BLE, all these things. And then at the network layer, uh, the most popular adaptation used here is the 6LoWPAN. 6LoWPAN is actually the IPv6 low power wireless personal area network, which defines the encapsulation and header compression mechanism over IPv6, because IPv6 cannot be used here, which requires more resources to suppress that requirement. The constant version of it is the 6LoWPAN. And similarly, in the transport, it's UDP, and then different type of application layer protocols like COAP, MQTT, etc. are used. Another very popular protocol is REST, which is very good for IoT based application, where because here any device or sensors or any component can easily provide state information to the application layer. So that is the small change or some small adaptation in the protocol stack for IoT. Now, this diagram is depicting the basic architecture of any IoT system. So what we need in an IoT device, we need three things. One is this sensor and actuators. Then we need a little bit processing power and the communication part. All these three things are available here. Say these are the IoT devices. They can be connected with the local network. In the local network, that can also act as a gateway. So basically, it has two interfaces. One interface is connecting with this, that means this communication and this communication module can be interacted. And there is another communication module, this part, that is actually connected with the backend services. So in this way, over the internet or Wi-Fi, whatever. So in this way, the local IoT nodes can be connected with some node where the backend service could be running in the cloud environment, or say any remote node can communicate with this local IoT system and can control its different components. This one is the ThingsPort, which is actually an open source IoT platform. So here you will get an idea how this IoT devices are connected with the user, or how it is actually um, linked with a IoT platform. So here you can see that different type of IoT devices are here, and this one is the IoT gateway. This IoT devices can communicate using different type of application layer protocols like MQTT, COAP, or HTTP with the ThingsPort platform. In the ThingsPort platform, it has two ends. One end is the rule engine, which is actually communicating with the communication gateway of that IoT system, and another endpoint, which is actually connected through HTTP or web socket and providing the access to the different visualization of the dashboard. So this end user are actually accessing the real-time services from this dashboard. So this is how the components of IoT and the platform which is deployed in some remote location and interact with each other. Here you can assume that this block is actually deployed somewhere in the cloud, from where the user can access the visualization or the services remotely from that platform. It has no direct access to the IoT systems. It will get the real-time statistics through this visualization. So that is how ThinkSport platform um, connects IoT devices, end user, and the different analytics. In the current scenario, Google Cloud Platform as well as AWS Cloud, these two are other very prominent and popular cloud platform. So now, if you look at the architecture of this Google Cloud platform, you will also find the similarity with whatever we have discussed earlier. So this is the layer where you have the sensors. You can see different type of sensors are there. This one is the edge device for providing real-time response to the user. Here, what we have, we can run different type of lightweight machine learning models, and then if you need more powerful analysis behind that, then the data can move to the data analytics in the cloud. So this layer is for the more real-time response. This one is for the more accurate response, probably not that real time. In this data analytics plane, you can see that there is the cloud function. So this is the main component using which um, you can invoke a particular functions which can perform some action over the data. It can utilize the cloud big table, BigQuery, different type of cloud machine learning models also. So by sorry, by utilizing all these modules, it provide the basic data analytics, and then there is a plane called data usage, where it mainly provide the insight or the visualization of the extracts of the data which has been analyzed by the data analytics plane. This architecture is from the AWS. Here also the same kind of architecture. You can see that this is the thing, this one is the IoT gateway, and here you can say that you can define IoT rule action. For example, if the battery is low, then you can take some action based on that. You cannot continuously exploit the battery of the thing. You can periodically take the data, and you can define different type of IoT rule or action here. This data can be stored in the Amazon DynamoDB. This IAM rule, this means the identity and access management. So here different type of rules you can define. That data will be accessed by the AWS Lambda uh, via this IAM role, and AWS Lambda is pretty much same as the cloud functions, but in Google Cloud Platform, you have to write the cloud functions. I mean, how to invoke a particular function, or what type of analysis you want to perform on that data. The same thing you can do here as in AWS Lambda. And this is the AWS API gateway that will be invoked to get the access of that function, and it will return back the data visualization. So that data visualization will be seen in the real-time dashboard by the end users. So that is the AWS architecture. Now this one is actually the architecture designed by my research team, as we are working in different type of social good applications like air sense, noise sense, drive and road condition sensing, sense the city. These are some of the functions we have used. So we try to match our architecture so that it can be fit well with the Google Cloud Platform or AWS. Here you can see that we have this different type of sensors, smartphone as a sensor, citizen as a sensor, smart city, etc. Then the whole architecture is divided into two parts. One is the participatory sensing layer, another one is the computation layer. In the participatory sensing layer, we assume that the citizen or the people has the access to the sensors and via its smartphone. So in the smartphone, different type of applications are running. For example, this one is the air sense, noise sense, smart Sense the City or D&R Sense, they are accessing different type of census data. They are storing different type of sensor data which are required for these applications. And then there is this local processing. So this is the part, same as the previous architecture like this in the Google Cloud platform. We have used this as a edge device. The same thing used here as the local processing. So here what we can do, we can store the data using SQLite, and we can perform some real-time analytics and machine learning over that. Here we deploy some lightweight machine learning pre-trained model. We take the data, we filter it, parse it, do the pre-processing thing, feature extraction, and then we deploy this pre-trained model. Through this layer, we can get a very quick response. But for the better accuracy and for the betterment of the model, what we can do, we can deploy it in the cloud processing also. Here we have an API gateway, and there are some predictive analytics used in these applications, which are like this, like map generation model, context aware data cleaning, or stay point detection, trajectory mining, road condition detection, driving pattern detection, data fusion. So these are some of the models which are used by many of these applications like air sense, noise sense, data sense, D&R sense, and sense the city. For that, we have this separate functions, and these functions can use one or more of these models, and they can provide the output data as visualization by invoking this API gateway. So that is the architecture that we have used in our work. Now I'm coming to this air pollution. So if you look at the report published by Greenpeace, you can see that in different states of India, they either we have a very poor condition of the data. For example, the red one is indicating where the level exceeds twice Indian national standard, and this yellow one is showing exceeds Indian national standards, and the green one exceeds WHO guideline. So here you can see West Bengal is somewhere here. So see the some part exceeds twice Indian national standard, the rest of the part exceeds Indian national standard. So that is the condition of pollution data. This is another very interesting report which shows the coverage, air quality data coverage by state. So that is again a very poor. You can say most of the states, they don't have data, no data. But West Bengal, we have some data, some manual data. Uh, NCT of Delhi, here you can see the real-time data we have. The reason is because the Pollution Control Board have deployed around 32 or 35 number of pollution monitoring stations in NCT Delhi. So their coverage was quite good. So if you go by the report, online media reporting that uh, 39 of world's 50 most polluted cities are in India, and India is in position 3 for the overall air pollution, which is a tremendous situation. Now, if we want to do this study, air pollution monitoring, in India, we have some pollution control board, central pollution control board, state-wise deployment stations. And this is one map which is showing the stations that are deployed in a particular state. Here you can see that in Kolkata, probably we have 10 or 12 pollution deployment stations. The positive part of this is they can give a very accurate, high accurate data, very good quality data. But the downside is that they are very costly and there is a sparsity, because it is not possible to deploy pollution monitoring stations in every corner or in every junction of the traffic. But if we really want to analyze air pollution of a particular city, we need data from as much as point, right? So that is the problem. So one very obvious solution of this problem is the participatory sensing. We all have a smartphone nowadays. Along with there is one company called Caterpillar that is actually US-based infrastructure company. They equipped air pollution monitoring device within their smartphone to monitor the air pollution exposure of their workers. So in the current situation, probably the common smartphones are not having that type of modules, but I think in the next 5-10 years, probably we will be able to have that component in our smartphone also. So what is the idea of participatory sensing with pollution data? The idea is building a small IoT device called air quality monitoring device, which consists of particle density sensor to measure PM 2.5 and PM10, gas sensor MQ135 to measure NHD, NOx, benzene, smoke, CO2, etc., and a communication module, Bluetooth communication module for wireless communication. From the smartphone, we can get the other information like location, we can get the accelerometer proximity, context information, etc. So this is the IoT device. From this device, we can get different type of uh, level value of the pollutants along with the timestamp and the other context information, location information, proximity from the smartphone. So what are the steps we need to follow? The first step is data collection, which is a rigorous step, I mean, where we can involve citizens. Once we have the data, we need to pre-process the data by cleaning the data. We need to perform calibration and then the data analysis, where we can run different develop predictive models for spatial interpolation. Machine learning model can be used for data analysis and prediction also. So these are the different type of sensor data that we have collected here. This one is the Android app through which we have collected data. For here you can see these are the accelerometer data, location data is there, and the different AQI air quality index value calculated, PM 1.0, PM 2.5, and the different weather parameters are also considered here. We divided the site into three parts. One is the urban, semi-urban, and rural. So here we have considered the urban area, which is Jadavpur, surroundings of the Jadavpur University, and semi-urban area, Baruipur area, 8 square kilometer area in the Baruipur. So data collection, that we have to do in two ways. One is the participatory sensing data, where this IoT device uh, in in a backpack connected in a backpack and collecting the data in the indoor as well as in outdoor. And along with that, we are also taking the ground truth data. So these are the devices which are the standard devices. So this is very important to see the how good, because whether these sensors are always not in a good quality. They sometimes give very poor data. So for the calibration purpose as well as for the ground truth, collecting data in both ways are very important. So this is how we have taken the participatory data. Okay. Next, I'm coming to the calibration part. So the calibration means when we have a different type of sensors, we have a reference point, low cost sensor reading, and some ideal response. So when these two are very close to each other, we can say that we are getting a very good solution. But if it is not the case, that means the reference low cost sensor reading and the ideal response are not very close to each other. In that case, we need to build a calibration model and some plus minus threshold that we need to figure out that function, and then we have to calibrate the data according to that function so that we can analyze the data further. So calibration is one very important technique here. Next step is the data analysis. For data analysis, for this particular type of applications, we are talking about the spatial interpolation. A spatial interpolation can be divided into multiple types of techniques like non-geostatistical or geostatistical and the combination of both. In non-geostatistical, very popular methods like inverse distance weighting or the natural neighbors, these are some of the very popular techniques. In geostatistical, kriging is a very efficient technique, and there are different variants of kriging available, like simple kriging, ordinary kriging, or universal kriging. So these kriging techniques are very useful for the interpolation techniques for geostatistical data analysis. And we can also build a combination of this, which is known as regression kriging. This kriging technique can also be used for machine learning approaches like support vector machine or random forest neural network based models. So different techniques can be built for the analysis prediction of the data for this air pollution data. I'm giving a very brief view of the inverse distance weighting or the utilization of inverse distance weighting here. Suppose in this region, this green points are the known points, and this black point is the unknown value. So here the objective is to find out some value or interpolate some value for this unknown value, right? So in the inverse distance weighting, the idea is try to predict a value at a location xy where it has the number of nearest known points which are surrounding to the xy to a known radius, say, and then that value will be weighted assigned to each known point value. That means that will be multiplied by a particular weight, and after that so this is the part where you can see this thing. So this weight, this is actually the wi, which is a known point for which weight assigned to this known point, and lambda I is the weight assigned for that known point. And how to get this lambda I? Lambda I is actually the inverse distance, that is 1 by di to the power p, where p is the power parameter which influences the weighting of wi on w. So if it is close to that known point, then the value will be very high. If it is far from the known point, the value will be less. So that is the very simple meaning of how to utilize this lambda for the inverse distance weighting. The kriging technique is the another popular approach used here, which is actually based on the use of semivariance, where the semivariance used to measure the spatial correlation. So how the semivariance can be estimated? Here 2 points, say two known values at 2 points. One is say xi and another one is xi plus h, that is separated by a distance h. So for that, we'll calculate the semivariance. And once we get that semivariance, the kriging technique will try to interpolate that spatial correlation in respect to that semivariance. So these are two model, like one is the spherical model and another one is the exponential model. Once we get the different points, semivariance as a function of distance, and then we will try to fit a particular model here. Here you can see that spherical and exponential two models are used to fit that function of distance here. Next is the estimated value that in the kriging that we are trying to interpolate for any point of interest, say x0, which is calculated like this. So here for this particular point, we are calculating zx0, and mu is a known stationary mean, which is actually assumed to be constant over the whole domain. And lambda I is the kriging weight. This one is the kriging weight with that we have discussed earlier. So that will be multiplied with this z of xi for the unknown point, for the known points, and minus uh, stationary mean of the unknown point. So in this way, kriging will be able to get the value of that point of interest x0. Different variants of kriging techniques like ordinary kriging, simple kriging, universal kriging. I'm not going into that parts. let me come to the result part, as I don't have much time. So these are the visualization. Here you can see that by using that AQMD device, this is the pollution footprint in Kolkata city when one of our volunteer takes a bus ride. And this is the AQM map to map for our indoor environment and AQM map for outdoor environment. Here you can see that it's a visualization of air pollution map of the neighborhood of Jadavpur area, applying the cleaning technique. This is one case study performed during Diwali, and at 7 to 7:30 p.m. We got this type of AQI values, but at 8 to 8:30 p.m. There will be a hike of almost 50 to 60 plus 60 AQI values. There's one another case study to study the effect of Amphan on air quality. Here you can see this 2020 and 2019 uh, data. So basically, the red one dotted line is PM10 and blue dotted is PM2.5 for 2019, and the red dotted is for red solid is PM10 and red is the PM2.5. So during Amphan, there is a dip in the pollution, but pre and post Amphan scenario, again, taken high. This one is the effect of bulbul on air quality. So here also you can see pre-bulbul scenario and post-bulbul scenario. This one is the funny storm that landfall near Puri, Odisha. So here you can also see during funny, pre-funny and post-funny scenario. But these analyses are not based on participatory sensing. Last four analyses are not based on participatory sensing. They are based on station data. This is the visualization where you can pick the service, air pollution map or noise pollution map, what you want to see, or the area. You also need to mention the session, whether morning session, evening or afternoon session. Another case study we performed, which is on visualization of less polluted route. So in Jadavpur University, from gate number 1 to gate number 4, we have three route to reach gate number 1 to gate number 4. And we have collected pollution data and the noise data also. And then we have it's nothing but the route optimization problem. So in this problem, we have considered the air pollution and noise pollution. You can also consider the road condition, traffic, and many other factors for that. So pollution could be one important factor there for the route optimization. Here's one thing. So as I'm almost at the end of the talk, it's 4 already. So just let me briefly tell you the opportunities. So the opportunities of this type of applications that where we can use a very low cost solution like IoT devices or the smartphones, which are actually very low cost. We don't need uh, to make much investment for the resources. Another is the participatory sensing, where the human involvement is there. So large number of individuals can extract and share information. We can keep the human or the citizen in the loop that can make the system more effective. Mobility, as the major problem with the standalone or the standard pollution deployment stations is that the sparsity of the data. We cannot deploy a pollution monitoring station in every corner of the city. So with the help of participative sensing and lightweight low-cost IoT devices, and by exploiting the human mobility, we can improve sensing coverage and data transmission. In very simple words, it will be easily scalable, extensible, flexible, and easy to maintain. So these are some of the uh, plus side or the opportunities of this kind of solution. But there are some challenges also. The first challenge is definitely privacy concern. When we are keeping the users or citizens in the loop, users may not want to share their sensory data or some of their private or sensitive information. For example, they probably don't want to share the current location, GPS location. Second aspect is that while participating in this type of ventures, mobile users consume their own resources. They are utilizing their own resources, battery, computing power, and have potential privacy threats. Why will they do this kind of participation if there is no significant incentive? So designing incentive mechanisms for participants is also a very essential challenge. Sensing quality is very in this kind of applications, you need to rely on IoT device and sensors, and these sensors are usually very low cost, not so reliable sensors. While doing these experiments, we are facing a lot of problems with the quality of the sensors and the longevity of the sensors. So their coverage, latency, and the confidence, these are big issues. Another challenge is the context. Sensor data can change. I mean, it depends on the uh, participant who is utilizing that IoT device, who is using that IoT device for capturing that data. For example, sometimes we are using our mobile or a smartphone, and probably we don't have much battery in the smartphone, or we are randomly moving from one location to another location. We can change the position of the smartphone or the preferences. So these things, this different type of context can also hamper the quality of the data. So these are some of the challenges when you're building this kind of solutions. You also need to keep these things in mind. So there are some of the references from my research team. If you're interested, you can go through it. Now I'm done for the content part. So if you have any questions, you can take the question.
Thank you, ma'am, for the wonderful, knowledge about the topic. Ma'am, there are few questions in the chat box, so I'm reading out few of them. Like we have a question from Ananta Madam, and it is about what are the name of the various sensors used for measuring temperature and humidity.
Wait, Acha. What are the name of various practical sensor used? So there are different type of sensors available, like MQ316. Some sensors are equipped with more than one. Some devices components are actually equipped with more than one sensors that can measure the temperature and humidity also.
All right.
To
Thank
collect
you,
the
ma'am.
data manually, is there any initiative from the government side? Uh, so there is some initiative from the government side. If you follow the uh, Pollution Control Board website, you will find they have very good data collection uh, from their deployed station. But the problem is that for LCT Delhi, you will get a very good data because they have a very good coverage. They have, I guess, 32 to 36 number of stations deployed in NCT Delhi. In Kolkata, we have 10 or 12 working at this moment of time. So this station data are available for research purpose. I mean, if you want to study the environment, if you simply want to study the different weather or different type of pollutant uh, data, the nature of the pollutant data, their change or the effect of the change in the environment for long term or short term forecasting, all these things, that then the um, station data is good. But the problem with the station data is the scarcity. They are very good quality data, but the scarcity is the problem. So for the sparsity, you have data for a specific location point, not all. But if you want to do a very high granular study on pollution, then you need spatially, uh, I mean, high granular data. not only temporal high granular, you need spatially high granular data. Usually, this pollution control board are having temporally high granular data, but not spatially always. That is actually the problem.
Thank you, ma'am. Uh, Thank you for
These
the
sensors are not very costly. As there are some questions, I can read them. I am trying to answer
right,
it.
right.
How much costly are these sensors? See, these sensors are not very costly. Usually, they can 200 to 500 bucks cost, but the microcontroller or the developer board, these are actually the costly thing. If you want to go to purchase a good developer board or microcontroller board where you want to run your lightweight AI model, then it will be cost you something around 10,000 uh, or maybe more than that. Otherwise, 2 to 5,000 you will find good microcontroller developer board. Among the two different models, which is one more effective? How can we understand which two model? Uh, Shagota Dash, can you tell me talking about which two model? Two different models, which is one more effective? Are you talking about the kriging technique or participatory sensing and the stationary data? Little bit confused for this question. Yes,
Shagota Das, if you're here, you can write in the chat box.
yes, ma'am. For okay, uh, can you mention which models you're asking about? Okay, so kriging is actually more. What I can say, kriging gives a better spatio interpolation because it has different variants based on the nature of the application. So you can figure out by analyzing the initial level of your data, you can analyze it and you can determine which particular model is better for your application. So rigging is little bit better, but again it's very hard to say that any one model is actually very good because it hugely depends on the nature of the data. Okay, so yes. Is there any other question?
No, ma'am, in the chat box, we do not have any more question yet. If there is any more questions, participants, you can write in the chat box. All right. So with this, we come to the end of the FDP. It was 1 second. Yeah, yeah. It was indeed an enriching session, ma'am, with your experience and your work that you have projected to us, and we have learned a lot about the knowledge-based systems, particularly for the air pollution problem. I'm sure we have all learned a lot from today's session, and this will help us to improve our skill. With this, we come to the end of our first uh, session for the 5-day long FDP program. Thank you once again, ma'am, for your presence and giving us time and accepting our invitation, first of all. So, I would like to share a certificate as a token of appreciation to ma'am. So, give me 2 minutes. Am I, is my screen visible?
Yes, yes. Thank you so much.
Yeah, ma'am. If you could kindly accept this certificate as a token of appreciation from our side, we will also be, sending a mail and give the physical copy to you. Thank you so much for being here in the session, and we have totally thoroughly enjoyed the session with a lot of knowledge about the new developments in this field. Thank you, everybody, and thank you,
Thank you.
ma'am, for your
Thank you.
presence.
Thank you. My pleasure.
Thank you, ma'am. I would now request the participants to kindly look in the chat box where the attendance link has been shared. The attendance link will not be shared in the WhatsApp group, and I would request all of you to check the chat box and take the attendance for the day, which will be active for a few more minutes.
Shall I leave?
Yeah, ma'am, you may.
Okay.
Thank
Thank
you,
you so
ma'am.
much.
Thank you so much for your presence, and we hope to see you again in some FDP or in other sessions.
Sure. Okay.
Thank you,
Take care.
ma'am.
Bye.
Bye.